we're going to show you what this product can do in the context of a specific example of a social media analytics use case. What's happening in this demo is a Twitter feed is coming in through a Kafka topic, and sentiment analysis subsystem basically takes the data and processes it. There is some pre-processing of the data, and then there is the real-time sentiment analysis scoring that takes place. You then move the data through a queue into a persistent subsystem, which again, all of these subsystems are stream analytics subsystems. They are strong topologies that are built and wired in a drag and drop fashion, which you'll see. And the persistence layer essentially persists the data into either Hadoop or NoSQL. In this case, we're persisting into Hadoop and to an index. And so you now have the data landing into both a real-time system as well as a batch system, and you can do both types of analysis. So we do real-time sentiment analysis. We do batch-based topic modeling, and we're able to congregate both of those. And we're even, in fact, able to do interaction between the two, where we actually build a model on Hadoop and update the model in real time into the top system, which is a real-time system, so that you can actually have predictive models being upgraded, being in a live manner without any downtime. So we're going to see how this looks in the form of a UI, and Puneet's going to tell us that.
What we see here is a social media analytics application built over the Stream Analytics platform. On the dashboard here, we see real-time widgets, which are being powered by the Stream Analytics platform. What's happening behind the scenes is the Twitter data is streaming into Kafka. A real-time pipeline is reading the data from Kafka. It is extracting the content from this Twitter feeds, applying a sentiment score on these tweets, the sentiment score ranging from a -1 to a +1, negative being the most extreme and +1 being the most positive. As the score is being calculated in real time, it is also being streamed via WebSockets to this web browser here. And using visualization techniques, we read the data of these WebSockets and plot the graph. On the left, we see a distribution pie chart. This pie chart reflects the average distribution of positive and negative sentiments over a sliding window. The platform is capable of performing such CEP queries with ease. And during the later part of the demo, we'll see how we can build such a pipeline where we want to perform complex event processing, pattern detection, aggregated averages, scores, etc. As I scroll down, we also see a different visualization of the sentiments and an aggregation on the right with the total positives and negatives again over a window of 30 seconds. The real-time pipeline also does topic classification of these tweets. So as the tweets keep coming in real time, along with calculating the sentiment score, the system also analyzes and classifies the tweet to one of the topics. For example, is the tweet about sports? Is the tweet talking about finance, entertainment, etc.? All of this happens in real time, and again, via WebSockets, we publish it to this real-time dashboard. Once the score calculation and topic classification happens, the tweet is also written into HDFS store. There are batch jobs running over the HDFS store, which does topic categorization, which also builds the sentiment model such that the model itself continuously evolves to provide more accuracy with more and more recent data. And as the model is calculated and scored via the batch jobs, they are immediately transferred to the real-time pipeline via the orchestration layer that the platform, Stream Analytics platform, supports. I'll move on to the topic tab. And here, as I scroll down, we can see the topic clustering. So the batch jobs are providing topic clustering on the data that's written into HDFS. And as I expand, we can see how those tweets for these particular topics are spread or tweeted from various different geographical locations. It gives a summary of the tweet sentiments for that particular topic clustering, the word cloud, some of the tweets as examples, etc. I'll now switch to the platform which powers this entire social media analytics application, to the Stream Analytics platform. And I'll quickly take you through the real-time pipeline that we built in order to power the social media analytics application that we just saw. Here we have a canvas in which we see different components connected with each other. This is the canvas where we build real-time applications. A real-time application consists of three components: channels, processors, and emitters. Channels is the one that acts as the source of data for the pipeline. Kafka and RabbitMQ being out-of-the-box connectors. And if one needs to connect to any other source, for example, IBM NQ systems or web services database, they can use the custom channel. Next is the processors. Processors are the main operators where all the processing logic that acts in real time exists. We have processors for CEP, that is complex event processing. We'll go into some of these in a moment. Next is the custom processor, which allows us to embed our own business logic into the pipeline in real time. For instance, if I want to execute a proprietary algorithm in real time on a Storm cluster, all I need to do is drag in the custom processor on this canvas here, connect it anywhere in the pipeline based on the logical flow. I can right-click on it, and here I can provide the name of the Java class which contains that specific logic that I would want to execute. As a developer, I need not worry about how this would get translated or how this would execute on a Storm cluster. The platform takes care of it. Hence, the statement Apache Storm made easy. As a developer, I can drag multiple such components, write my own logic, or use the operators that are already available. For instance, if I want to filter the incoming data, I can drag in the filter processor. If I want to write data into HDFS, I can drag in the HDFS processor, connect it in the pipeline. Similarly, if I want to index the data into Elasticsearch or Solr, write data into a NoSQL store like HBase or Cassandra. If I have any predictive models written in R or SAS, I can export those as PMML and use the PMML operator. Similarly, if I want to create micro batches based on certain time thresholds, I can drag in the timer processor. The alert processor allows us to go ahead and generate alerts or trigger workflows based on certain criteria. Let's take up one more example of complex event processing, CEP. Let's say I have data that's streaming in and I want to calculate an average over a sliding window. I can drag in the statistical CEP. I can connect it in the pipeline. I can right-click on it. And as part of query here, I select the message, select the field over which I wish to calculate the average, min, max, sum, any of these operators. Select the time window being fixed length or sliding, provide the duration, and the platform would take care of the rest. The platform would execute with every incoming event over this window, calculate the score, whether it be average, sum, min, or max, and provide it to the pipeline for further processing, which could be persisting it into a NoSQL store or HDFS, or even publishing it out to Kafka or RabbitMQ for that matter.
And this would address, I think, some questions that are coming up on whether you can actually query ad hoc on the stream without writing any code. And the answer would be yes. And this is the mechanism that you would use.
So CEP also allows us to bring in a custom CEP processor. This processor gives us the ability to write CEP queries on the streams as they keep coming in. So for example, I just right click and here I can provide an entire SQL query of operations that I would want to do, provide the time window, any kind of pattern detection, alerts, triggers, etc. could be done easily using the CEP processor out here. Next category is emitters. Emitters allow us to emit the data out of the pipeline. So for example, once the processing has been done, I can use the Kafka emitter to emit to a Kafka topic for some other downstream system to consume. Similarly, I can emit to a RabbitMQ. The streaming emitter publishes the data to WebSockets. So if there are any real-time dashboards that we would like to power, we can use the streaming emitter and the real-time dashboards can read off the WebSockets and provide visualizations. Once this entire pipeline is created by drag dropping these different components, I can hit save and the system would bring me back to this screen here. From here, I can submit that pipeline to a Storm cluster. I can stop an existing pipeline from running. I can pause the pipeline, etc. So all operations that I need to do as an operations or a developer, all of that could be taken care from the UI itself. I need not be, as a developer, I need not know how Apache Storm works or how Kafka works, how to read the data from Kafka right into Elasticsearch, Solr, etc. All that the platform would take care of. I would want to know how many events per second is the pipeline able to process. What is the processing time for each of those individual components on the cluster? For instance, out here in the monitoring view, for the pipeline sentiment analysis, we can see the processing time for all the individual components. I can go ahead and select more view types. The throughput view would give me an idea about how many events per second it is being able to process at individual component level. Similarly, I can find out the application or the infrastructure errors, that is how many events failed either due to a hardware problem or software problem or due to a business logic problem. So all of this monitoring is available, and not just in ways of graphs, but I can also set up alerts for those. For instance, I can set up an alert wherein I can say, raise an alert when the threshold or when the events per second drops by 5% or 10%. So this allows me to get instant notification if the pipeline slows down or if there are certain errors in the pipeline, etc.